Guten Tag, I'm Fumeng. I will still talk about scatter plots, but mine is a personal story about the research process. About 10 years ago in 2013, I started my graduate school at Tufts University. The very first research project I worked on began with this visualization perception problem. Between the two side-by-side scatter plots, which one shows a more correlated dataset. This problem is both simple and difficult. It is simple because as long as you know a bit about correlation, you can make the right judgment. It is difficult because you are unlikely to calculate correlation values from the scatter plots. Instead, you might look for visualization features such as prediction ellipse when making your judgments. From 2015 to 2017, we did a follow-up paper on this. Using largest regressions and features proposed in the literature, we found that some features slightly better predict people's judgments than correlation values, suggesting that they might be the feature people were looking for when making their judgments. However, I did not continue this topic because I joined Brown University as a new PhD student in 2016. The opportunity at Brown came 2 years later. Daniel Hong was invited to give a talk at our group seminar when he talked about his paper, Evaluating Graphic Perceptions with CNNs, which later largely motivated our current work. After 2018, unfortunately, it was COVID-19 pandemic. Like many other people, I was locked at home, but therefore had more time to think about research. This topic about visualization perception, visualization features, and whether we can predict people's perceptual judgments often came back to my mind. More specifically, I was thinking, the methods we use to extract visualization features rely on many previous studies. Our methods may not apply to other visualizations or tasks because we may not have enough prior work. Second, suppose the methods apply. If we change the scatter plot slightly, we have to recollect the data and refit the model. Can we have a model that can give us good predictions of people's perceptual judgments for different visualizations and tasks, such that we don't have to do the same thing again? Third, even more ambitiously, can we have a model of human vision which can answer all our questions about visualization perception? In a typical visualization perception study, the direct connection between us, the researchers, and participants is visualization image. In our case, the two side-by-side scatter plots. Perhaps we should start with this direct connection. Convolutional networks came to my mind because they are designed to extract features from a large set of images to solve vision tasks, and some neuroscience papers seem to suggest that they could be a biological model for human vision. With this in my mind, like many other PhD students, the first person I talked to is my PhD supervisor, David Lidlaw. David told me that there isn't very much work using networks for solving visualization perception problems, so this could be interesting to study. I also talked to one of my PhD committee members, James Tompkin, whose name also came up earlier in this presentation. James told us very firmly, first, these networks are not human vision models. And second, their CNN papers show that basically CNNs cannot solve graphic perception, but they did not try scatter plots very much, nor human judgments, so this could be interesting to continue. With double permissions, I started to work on this project. The first thing I did was to grab the dataset from the 2015 project and reproduce all the visualization images. The purpose was to decide which architectures we were going to use and the values of all hyperparameters. More formally, the goal of our study 1 was to predict people's left and right judgments for which one shows a more correlated dataset between the two scatter plots. We then recollect the judgment data through prolific and repeat partition, initialization, and training 10 times to get bootstrap confidence intervals for prediction accuracy. Before we can interpret the results, we have logistic regressions which use left and right correlation values as predictors. They know correlation but don't see visualization images as neural networks do. They provide us baselines to understand the prediction accuracies of neural network. The results of our study 1 shows that the 4 logistic regressions, 2 VGGs, 2 anti-aliased VGGs, and our own design VCCs have similar prediction accuracy. This tells us that CNNs can predict people's correlation judgments in scatter plots, at least for our dataset. Recall that what we really want is to have a model that can give us predictions even we change the scatter plots slightly. Therefore, we decided that in our next study, we were going to test these models on different datasets. Lin Harrison, a collaborator of previous papers, shared his preliminary study and helped it decide that, first, we increase the number of dots in each scatter plot from 100 to 200. Second, we show 5 outliers in each scatter plot. We then collect the 2 datasets and use the model from study 1 to predict the new test sets without fine-tuning or refitting. We also retrain these architectures on the new training and validation sets in order to make a fair comparison. Surprisingly, the results of study 2 show that logistic regressions do not generalize very well. Their prediction accuracies decreased very much. On the other hand, VG19 and anti-aliased VG19 generalized reasonably. On average, their prediction accuracies decreased only slightly. So, logistic regressions essentially learn a threshold between left and right when making predictions. They do not know that the input is different. On the other hand, CNNs know that the input is different, but the problem is that we do not know this black box enough in order to explain their generalizability. Therefore, we follow up on this and decided to explore explanations for these neural network models as our study 3. Yuxin, a friend of mine, who also has papers on similar topics, suggests feature visualization. Feature visualization is an image that can activate a neural network model the most, and these images are considered features learned by the model. We use a VG19 model and compute 4 feature visualizations for each neuron in each layer, and then cluster them layer by layer. And we also did the same thing for the models trained on the other 2 datasets, but found that the images are similar. So our study 3 shows that in deeper layers, there are interpretable features such as Gaussian kernels, correlation lines, and dots. Gaussian kernels may suggest that besides prediction ellipse, people also need density information when making their judgments. I'm not going to explain each feature here. Please refer to our paper and supplementary materials. Importantly, this process does not rely on hypotheses to extract visualization features. And because features were similar across different datasets, they partially explained the model's generalizability. And that was the middle of 2022. This is a very brief overview of our paper. I'll say our 10 years of thinking about this problem in 10 minutes. To summarize, With our prior knowledge on correlation perception in scatter plots, we think CNNs can predict people's perceptual judgments, extract plausible features, and have some generalizability. We also think that this way of studying with visualization images and thinking about the perception problem backwards seems to be an inspiring way that can introduce new insights. And last, we feel that visualization perception study is a circular process, and our results may inform model selections for future studies. And thank you so much for listening. I'm happy to answer any questions.